Covalent bonds are formed when atoms share their valence electrons. Yet sometimes that sharing can turn into stealing. Let's take a quick look at the periodic table again. What we can see here are the top few atoms that we have already been talking about. What we want to pay attention to this time is that as we move to the right, atoms have more and more protons in their nucleus, and more electrons in the corresponding electron shells. What charge does the nucleus of an atom have? That's right, it's positive. And the more protons that get packed in there, the more positive charges the atom is carrying. So the leftmost atoms in row 1, like lithium, have less protons and thus less positive charges in their nucleus than atoms in row 1 on the far right side, like fluorine. Lithium has 3 protons and 3 positive charges. Fluorine has 9 protons in its nucleus and thus 9 positive charges. Because the nucleus of an atom behaves similar to one side of a magnet, we can imagine that fluorine's nucleus is a bigger magnet than lithium's because it has more charges. We also know that electrons are negatively charged and are attracted to the positive charges in the nucleus of an atom. Which atom do you think has a stronger attraction for electrons? That's right, fluorine does. This ability to more strongly attract electrons is called electronegativity. Atoms that are colored green in this periodic table are less electronegative than those that are colored red. Interestingly, as atoms get really large, like those down in the 4th and 5th rows, they add more and more electron shells. That means that even though the nucleus has more charges, the size of the electron cloud surrounding it actually reduces the attraction they have for those outer electrons. This is why the most electronegative atoms tend to be towards the right and up at the top. They have more positive charges in the nucleus and only have 2 or 3 electron shells that could block the attraction. What does this mean in practical terms? It means that atoms with different electronegativity values more strongly attract electrons when they are being shared. Again, quantum mechanics jumps in here and makes things a little complicated, but you don't need to know all the fancy equations. What you need to know is that some atoms are greedy and take more than their even portion of shared electrons. Let's take a look at water. Good old H2O. Water has 1 oxygen atom and 2 hydrogen atoms. When we look at our periodic table, we see that hydrogen is much less electronegative than oxygen. That means instead of sharing electrons evenly like this, they are shared unevenly, more like this. Look at that oxygen being stingy. What is happening is that oxygen is taking more than its fair share of the negative electrons and leaving the hydrogen nucleus to be slightly exposed. This makes what chemists call a polar bond. Because oxygen tends to be a little more negative and hydrogen tends to be a little more positive. The fancy word for this is dipole moment. This little delta symbol is used when there is only a fraction of a charge. But that just means that the electrons are spending more time with oxygen and less time with hydrogen. This difference can be large, as in water, or it can be small, as in methane. Check it out. Carbon is only a little more electronegative than hydrogen, according to the periodic table. So the bonds in methane are not strongly polar. And the bonds between identical atoms are not polar at all because they're sharing evenly. All of this talk about polar molecules will become much more important later when we talk about hydrogen bonding. So oxygen and hydrogen produce a pretty strong polar bond. But what would you imagine would happen between atoms with an even more dramatic difference in electronegativity? Let's look at chlorine and sodium. Sodium has one of the weakest electronegativities, and chlorine is one of the strongest. As an atom of sodium and an atom of chlorine approach each other, the difference is so great that chlorine flat out steals sodium's valence electron. No sharing for this bully. However, notice that because sodium lost the only electron in that last shell, it now has a full shell beneath. In fact, both of these atoms now have full outer electron shells. They're kind of happy this way. What's even more interesting is that because chlorine has one more electron than it has protons, it's negatively charged, and now referred to as chloride. It has become what chemists call an ion. Ions, as we mentioned previously, are just charged atoms with more or less electrons than protons. Atoms with more electrons are negatively charged and referred to more specifically as an anion. Anion are just ions with a negative charge. What about our friend sodium? Sodium has one less electron than proton, and thus has a positive charge. Positively charged ions are called cations, as in, I'm positive my cat is out to get me. Now that chloride has a negative charge and sodium has a positive charge, they stick together. This is called an ionic bond. Ionic bonds occur between oppositely charged ions, or between cations and anions. In real life, we see these interactions in things like sodium chloride, or table salt. Table salt is an ionic compound. It's made up of a lattice of sodium and chloride ions stuck together. Another ionic compound that many people are familiar with is MSG, or monosodium glutamate. Glutamate is an anionic amino acid that we will meet again later. And once sodium loses its electron, it becomes positively charged and they form MSG. Now, we've looked at the two most powerful atomic bonds, the covalent bond, where atoms share electrons, and the ionic bond, where one atom loses an electron and another one gains an electron. The next type of chemical bond on our list is called a hydrogen bond, and it's based on a concept we've seen before. It's based on the fact that some covalent bonds are polar. Here's our old friend H2O. Oxygen is more electronegative than hydrogen, so this is what the charges look like. Hydrogen is slightly positive, and oxygen is slightly negative. Hydrogen bonds occur when a hydrogen atom is trapped between two electronegative atoms. Here we have two water molecules, each with tiny charges on the oxygen and hydrogens. Now if they line up like this, we see that the tiny charges will attract and form a very weak bond. When H2O is a gas, often called steam, there are very few, if any, of these hydrogen bonds. Hydrogen bonds are too weak to withstand all that energy of motion, kinetic energy. However, in liquid water, there are many more of these hydrogen bonds forming and breaking. In ice, all the possible hydrogen bonds are formed, and there are enough of them to keep the structure solid, but only at a lower temperature and energy. We will come back to this concept later, because it is important how water reacts when it freezes. The ability for water to participate in these various quantities of hydrogen bonding is one of the fundamental principles that makes life possible. First, it allows for cohesion. That is when molecules of a particular kind stick together. This allows trees to take up water against the force of gravity. Water molecules that are evaporating off the top of the tree are still hydrogen bonded to the water molecules below it. This pulls the water molecules up through the tree. Additionally, hydrogen bonds allow for adhesion, which is when two different molecules tend to stick together, as opposed to cohesion, which is two of the same molecules sticking together. This happens between the tree itself and the water molecules, which also helps resist the pull of gravity. The polar nature of water also has other consequences. It is the reason that some substances dissolve in water and others don't. There is a rule in chemistry: like dissolves like. Water is polar and therefore has tiny partial charges. This makes it easier to dissolve polar and charged molecules in water. If we place a chunk of salt into water, it will slowly dissolve. When we dissolve one substance into another, we call the result a solution. The dissolving agent is called a solvent, and the dissolved molecules are called the solute. The polarity of water makes it a great universal solvent. Again, it is particularly good at dissolving polar and charged molecules. That is because it can form hydration shells around the solutes. The partial charges from the polar water will line up and attract to the opposite charges of the solute. This works for non-charged polar molecules as well, like sugar. The dipole moments of the surrounding water molecules will line up and form hydration shells with the partial charges of the polar molecule. This is why oil does not dissolve in water. It has no charged or polar bonds, and so it tends to resist the formation of hydration shells. Substances that resist dissolving in water are called hydrophobic, whereas the salt or sugar molecules that do dissolve in water are called hydrophilic. Hydro means water, and phobia means fear. Thus, hydrophobic molecules are afraid of water, where philic means love, so hydrophilic molecules love water. The weakest of the chemical bonds are van der Waals forces. Van der Waals forces occur when atoms are pressed very close together, and the electrons rearrange briefly to allow a bond to occur. These bonds are extremely weak by themselves, but given enough of them, they can hold hundreds of pounds of weight against a wall. These are our chemical bonds. Something that is related to chemical bonds, and that we have taken for granted up until now, is that atoms and bonds arrange themselves in particular ways. This is a complicated process that has to do with the combined interactions of all the electrons. But let's take a look at some of the important molecules and the shapes that they form. We've seen water, which has a V shape, like this. Nitrogen and hydrogen form a shape kind of like a tricycle. We saw a three-dimensional diagram of methane earlier, but now we want to really focus on the shape of this molecule. When carbon forms all four single bonds, it makes a tetrahedron, a pyramid shape like this. We can put any atoms on the ends of these bonds, but the shape remains the same as long as there are four single bonds. Carbon can also form double bonds, like in carbon dioxide, which is linear because of the double bonds. Remember that double bonds are when atoms share two electrons with each other. Carbon can double bond with itself, like in this molecule called ethylene, which is produced by fruit to make it ripen. Again, it is important to notice that carbon can form an almost endless variety of bonds with other molecules. This is the reason we are carbon-based life forms. It is the vast array of molecular structures that carbon is capable of making that allows life to be possible.